Okay, the atomic structure unit, we're going to be doing a lot of things with periodic trends and things, but we do need to review the basic anatomy of the atom and the basic ideas of electron configuration and orbital diagrams. So that is your work for the weekend, and then you're going to have a quiz on it. You might want to read through that first page that says a basic review of atomic structure and catch all the stuff that's on there. It's all review from last year. The basic idea is that where the electrons are in an atom, all that empty space, is essentially made up of what are called principal energy levels. Those principal energy levels are then made up of sublevels. Those sublevels are made up of orbitals, and then the electrons live in the orbitals. If you remember from last year, if your teacher taught it to you this way, I know I did with the apartment analogy, it really is helpful to think of it like an apartment, a high-rise apartment building, where the principal energy levels are the same thing as the floors of the apartment building. The sublevels are the same thing as the actual apartments. Then the orbitals are the bedrooms in the apartment. And if you have an S-type apartment or an S-type orbital, there's only one bedroom. In that bedroom, 2 electrons can live. If there are 3 orbitals or 3-bedroom apartment, you could have 6 electrons there because there are 3 bedrooms, 2 electrons per bedroom. For D, there are 5 orbitals, so 5-bedroom type apartments, and for F, it was 7 bedrooms, so you could fit 14 electrons in an F-type orbital. So just kind of peruse back through all that information. In the lower left corner, you see what I have here on the screen, the order of filling for placement. We said last year if you walk up to the apartment building and ask to live there, you're going to always want to live in the lowest energy possible. So the lowest energy orbital is the 1s, then would come the 2s, then the 2p, then the 3s. So you see what I'm doing is I'm going to start at the bottom of an arrow. I'm going to fill the 1s, then I'm going to fill the 2s. Going to the bottom of the next arrow goes 2p and then 3s. Bottom of next arrow, 3p, 4s. Bottom of next arrow, 3d, 4p, 5s, etc. You would just keep going and going. You'll notice at the beginning it's very simple. 1s has less energy than 2s, and then 2p has more energy than 2s, and it seems to go in order. But once you get up to 4s, if you see 4s is here, the next place you're going to go, sorry, I don't know why that did that. 4s is here, the next place you're going to go is back down to 3 in the d orbital, and that's because d orbitals take more energy than s orbitals. So it's actually easier for an electron to be on the 4th energy level in an s-type orbital than the 3rd energy level in a d-type orbital. So read through that. Might be a good idea. Maybe get your notes out from last year, review that a little bit. What you need to be able to do skill-wise is draw orbital diagrams and electron configurations. If you remember, the difference between them is that an orbital diagram actually shows the electrons as little arrows, as you can see in your packet, and electron configurations don't. Electron configurations were the ones that went 1s2, 2s2, 2p6, 3s2, that type of thing. So one of your practice problems, let's go ahead and do one of those together. The first one that's there is aluminum. So first thing you have to do is figure out how many electrons aluminum has. So look at its atomic number. Whatever its atomic number is how many electrons it has as well, even though that's the number of protons, because it would have to be equal for it to be a neutral atom. So I have 13 electrons. So I'm going to start by filling and putting into the 1s orbital. So I'm going to write a 1s. I'm going to do a single line to represent the 1 orbital in 1s. Remember, this is a S-type apartment. It has 1 bedroom. So I can put 2 electrons. They have to have opposite spins, as you read on the first page in your 3 principles. By the way, those 3 principles on the first page, Aufbau, Pauli, and Hund's, you do need to know them and know them by definition. I'm very likely going to ask you, what is Hund's rule? What is the Aufbau principle? Because they like to do that on the AP test. Okay, so we put 2 electrons in. So far we've used 2 of the 13. The next orbital we'll fill is 2s. So I'll put 1 line because it's an s, write 2s underneath it, 1 arrow up, 1 arrow down. So now I've put 4 of my electrons. After 2s, go to the bottom of the next one, is 2p. Now p gets 3 lines. Again, s gets 1 line, p gets 3, d gets 5, and f gets 7. So I need to fill these. I'm going to be careful while I'm filling them, though, to follow Hund's rule. Okay, Hund's rule says that electrons will go unpaired in equal energy orbitals before they pair up. Okay, if you remember, this was if you had a 3-bedroom apartment with 3 rooms and 3 electrons need to live there, they're going to all go to their own room. They're not going to pair up with each other until they have to. But at this point, now they have to. I've used 7 electrons. I still have 6 left. So this will be 8, 9, and 10 will go like that. All right, so that's 2p. Then after 2p, if you look in your chart, comes 3s. So we're going to put 3s, single line. So far I've used 10 electrons, so I still have 3, so that'll be 11 and 12. After 3s comes 3p. When you do a p, you draw 3 lines, okay, and then you count, you see you only have 1 electron left. So I'm going to put him on one of the lines. Doesn't matter which line I put him on, doesn't matter if I made him pointing up or down. Okay, either way, it will be absolutely fine. So that's the basic idea of an orbital diagram. Again, we're going to write everything out. We're going to use lines to represent the orbitals, and which is why it's called an orbital diagram, and then arrows to represent the electrons. Okay, and by the way, when you look here, these numbers and letters, they represent the sublevel, and then the principal energy level can be seen by the first number there. Okay, the principal energy level can be seen by the first number. If it's a 2p apartment, you're on the 2nd floor. All right, so that is orbital diagrams. There's some more there for you to practice. If you look at the bottom of your paper, there is an answer key, so you can go back and check those. All right, let's do electron configurations now. Electron configurations uses the same arrow chart. By the way, you do need to know how to draw that arrow chart for yourself. It is not given on the exam, so please make sure that you do know how to draw that for yourself. And then let's start with the first one there, BE. Okay, BE, we want to figure out, well, that's not a very long one. Let's do a different one. Ooh, AU is really long. Do I feel up to it? No. Okay, let's do NA. Okay, we'll do NA, number 4. So NA has 11 protons, which means it has 11 electrons. So we have 11 electrons to deal with. So we always start with 1s. So we're going to write 1s. With orbital diagram, we put a line above it and drew an arrow up and an arrow down. We don't want to do that with this. With this, it's more of a summary. Electron configurations are a summary of the orbital diagram. And all you do is write in the upper right-hand corner how many electrons there were in that one. So if it was the orbital diagram, you would have done this. But we want the electron configuration, so we're just going to summarize it. So 1s2 is saying that there's 2 electrons in the 1s. After 1s comes 2s. So 2s, we still have 9 electrons left, so I can put the max of 2 in my s orbital. By the way, if you don't remember this, you can put a max of 2. Let's call this max. You can do a max of 2 in s. You can do a max of 6 in p. You can do a max of 10 in d, and a max of 14 in f. So far I've used 4. Still have 7 left. After 2s comes 2p. So 2p6. Going to max that one out. And then after 2p comes 3s. So far I have used, I can put 2 in 3s, but so far I've used 10. I only have 1 electron left. We'll call that 3s1. And then that's it. That's the electron configuration. The orbital diagram would have looked just like it. Would have just had the lines there and then 1 electron in that last 3s. So again, some practice problems there for you, and the answers are down at the bottom. So don't peek until you've tried them, and then you can go down to that point. All right, the last part of this is using abbreviated electron configurations, which can be really useful and handy because most of the time, all that we care about in an atom are the valence electrons. That's usually the only thing that we're really concerned with, is how many valence electrons there are. Valence electrons are the outermost electrons in an atom. Those are the ones that we are trying to look at. And so this abbreviated electron configuration is going to skip a lot of the electron configuration and leave you with only the outermost shells. Not necessarily just the outer one, but the outermost shells. So let's use zirconium as an example. So zirconium, Zr, has 40 electrons. Now we are going to have to make use of the periodic table to do this. So the directions up top, and you can always go back and access them. The directions up top tell us that we need to find the closest noble gas to zirconium that has fewer electrons. Okay, so zirconium is number 40. So the next closest noble gas with fewer electrons is krypton. So we're going to do Kr in these square brackets. Essentially what you're doing when you do that is you're skipping all of those electrons all the way through krypton. Essentially you're telling the reader, hey, I've just taken out the the electron configuration for krypton. And the cool thing is krypton has 36 electrons to it. 36. So out of your 40, by writing krypton in square brackets, you have already used 36 of 40 electrons. So now we only have 4 more left. Now, to decide where to pick up, because you've skipped 36 electrons with, here's what you do. Find zirconium again, number 40. Look and see what period it's in, what row number it's in. Look all the way to the left of zirconium and you will see a 5. That's telling you that it is 5th energy level. Okay, its valence electrons are 5th energy level. So you write a 5 down. Then it's always an S. So you're going to get the number for the energy level from what row it's in, and then it's an S. So we have an S there. So now we can start filling. So we are here already. This is where we're starting on our energy chart, is at 5S. We said we have 4 electrons left. So I'm going to do 2, okay, because I can put a max of 2 in an S. So 5S2. And then that still leaves me with 2 electrons. My next orbital is the 4D. That's the next one I'm going to use, 4D. And then we said we only have 2 left, so it'll be 4D2. So Kr parentheses in brackets, square brackets, and then 5s2, 4d2. Okay, it's a lot better than writing zirconium out. If you had written the full electron configuration for zirconium, it would have been 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d4. The abbreviated one sounds pretty awesome, doesn't it? Yeah, I agree. Let's try another one, just so that you can have another practice. Actually, we're going to try 2, because there's 2 things I want you to see. Let's go ahead and do potassium, the second one there on your list. So potassium has 19 electrons. Okay, so we're going to do closest noble gas to potassium is argon. Argon symbol is AR, square brackets. That uses 18 electrons. You don't have to write this number there, by the way. You can if you want, just as a notation to yourself. But it's me just acknowledging how many electrons I just used. I used 18 of the 19. I only have 1 more electron to place. So I find potassium. Potassium is 4th energy level. See what row it's in over there. K, 4th energy level. I'm going to put a 4 down, and then I'm going to put an S. It's always an S. And I only have 1 electron left, even though it can hold 2. I only have 1 left. So there's the electron configuration, abbreviated electron configuration for potassium. Now I do want to show you one more, because this is something that students like to try to do, try to cut corners. I want to make sure you understand why it's not okay to do. Let's use argon as our example. So if I ask you to write the abbreviated electron configuration for argon, argon has 18 electrons. Some students will do this and tell me that that's the abbreviated electron configuration for argon. That doesn't work because, well, multiple reasons. First of all, the rules say find the closest noble gas with fewer electrons. Okay, argon has the same number of electrons as itself, so that is not fewer, so that's breaking the rules. Plus, the point of these abbreviated electron configurations is to see the valence electrons, to see the outermost electrons on that electron configuration. So we can't see anything here, except for some square brackets. So the closest noble gas with fewer electrons, so no, is neon. Then we find argon, follow it all the way over to the far left side, and we see those valence electrons are on the 3rd energy level. And then it's always an S. Okay, so we're going to be starting here at 3S. So we have 2 electrons we can put there. Remember, neon used 10, so far I've used 12. After 3S comes 3P, and I have 6 left, because I've used 12, I have 18, so 3S2, 3P6. And again, you can see here, 3rd energy level is our outermost energy level, so there are 8 electrons in the outermost energy level. And the reason why that should make sense is this is argon, noble gas. We know noble gases have their octets full, so that is what we want to see, not that silly argon in square brackets thing. Okay, now there's some more problems again for you to try. Answer keys down at the bottom. Then there's 2 homework sheets for you to try, and answer keys to go with both of those. Any issues that you have, email me over the weekend. Come see me on in the morning so that you can go over it. Remember, you want to make sure that you are prepared for this quiz on the day that it says on your packet. All right, I will talk to you guys later.